Good morning, everyone. I sort of summarize maybe a little bit. I put this already on the board, what I said last time. So you're looking just one single Hamiltonian. I will stick to that sort of boundary condition. So we look at the Toda Hamiltonian. Here it's still written with this chain with the exponential interaction. And I also put here, repeated the definition of the Flaschka variables, which are sort of the convenient variables to do all this kind of analysis. So rather than looking at the P and Qs, we look at the stretch, which is the potential differences, positional differences, and you can also think about free volume. I mean, it's the volume between two neighboring sites. I mean, the volume which they sort of span, if you want so. And so this is, of course, a mistake. I mean, that would be an amazing choice of variables. No, I mean, the Bj is actually just identical to the momentum. I'm actually using A and B because that's what's always in the literature. Okay, and then the basic object which we discovered last time was the Lex matrix, which is just a triangle matrix, which is sort of along diagonal you have all the momenta, and along the two off diagonals we have this Flaschka HA, and it's obviously a symmetric matrix. And the main reason why this matrix is so important is that if you look at the eigenvalues of this matrix, I mean, this sort of gives us automatically all the conserved quantities of the Toda lattice at finite volume, let's say from 1 up to n. Okay, and so what we have to do today is sort of another piece of this hydrodynamic picture, which so far I didn't emphasize very much, but you know, something which, of course, you know from ordinary fluid. So if I look at an ordinary fluid, and if I want to write down sort of the hydrodynamic equation, you know, then the first postulate what you make, I mean, you have this fluid, and of course, it's a non-equilibrium phenomena, but, you know, the fluid is moving maybe in a very complicated way, maybe it's even turbulent. But even for a turbulent fluid, if I'm going to look at a very small volume, and I'm asking myself what is the statistics of the particles, then it's a very good approximation. It will be an equilibrium. It will be an Boltzmann or the Gibbs Ensemble, which I'm going to see. And the important point about this is that you know, there are just few parameters which characterize this ensemble, and of course, these few parameters are in one-to-one correspondence with the conserved quantities of the field. So for a real fluid, it would be density, it would be the momentum, it would be the energy. So I have 5 conserved quantities, and therefore the Gibbs ensemble is characterized by these 5 numbers. And when I look locally, of course, you know, these numbers are going to change in space and time. But you know, if I'm looking at a given time in some sort of sufficiently small region, I will see exactly that type of distribution. And so this idea, of course, we have to implement also for the Toda lattice. I mean, it's just otherwise, you know, we wouldn't properly call this hydrodynamics. Okay, and so now we have to think about how to do this. And of course, for the Toda lattice, I mean, we don't have 5 conserved quantities, we have an infinite number, and therefore your Gibbs ensemble must depend on an infinite number of parameters. And this is sort of what in the community is called the generalized Gibbs ensemble. So generalized just says that, you know, we have more chemical potentials than what we have, let's say, for an ordinary fluid. Okay, and so now we have to maybe write down some formulas. So, you know, I remind you that we had the conserved quantities, which were Qn. I mean, these are extensive quantities. And of course, in spirit, you know, if I write down formulas, maybe one should again sort of restrict. I mean, you know, when it's really important, I will put the restriction explicitly. Well, and then, you know, I'm just following Gibbs. I mean, then we introduce chemical potentials. Let me call mu n. Okay, and well, then if I have this, I mean, I can certainly write down what my Gibbs ensemble would be. I just sort of somewhat formally, I write e to the, usually the chemical potential comes with a plus sign, so I write here the summation n equals 0 up to infinity, and I put all the chemical potentials, and then I put here the extensive quantities, which are Qn. And that certainly will not be normalized, and maybe there are some conditions on the mu n that I can normalize. And then I put here the partition function, and that would be sort of my generalized Gibbs ensemble, right? Now, this is a sort of not a very convenient way to write it, because, you know, I have always this sum, and sort of looks a little bit messy, and so it's more convenient to sort of think as the mu n really, as a Taylor coefficient of a power series. And so let me introduce the chemical potential. So here I already used the word chemical potentials, but I'm sort of just reuse this word. I mean, just I want to put chemical potential, not to get confused with the mechanical potential, which of course has nothing to do with what I'm writing here. So this is chemical potential, and of course what I do is I call V of W. And now usually, one puts for the potential, and I mean for this potential, I want to put the minus sign. So I just write this as the sum. Sorry, this starts not at 0. I mean the conserved quantities start at 1. Okay, so it's 1 up to infinity, and then I have mu n, and that's just sort of the power. Okay. And then we have a nice way of writing this Gibbs ensemble. I mean, so first of all, there will be. I can rewrite this formula in an easy way. I mean, remember that the QNs, I mean, sort of just the sum over the eigenvalues, and the trace of this, it's a trace of the nth power of the Lax matrix, and then, if I put in this formula, you see that I just get the function of the Lax matrix, and so my Boltzmann weight will be simply the trace, and now I'm really careful. So, I really have a finite trace. I mean, there's this function V, the chemical potential, and then there's the trace, okay? So the Boltzmann, once I have all this notation, the Boltzmann weight for the generalized Gibbs ensemble looks very simple, okay? Is that fine enough? So I just use the fact that the Q super n is nothing else but trace L to the power n. And so, if I do a sum over here, then I will get just a function of that matrix. Okay, that's all what I'm using. Okay, but now I have sort of a nice compact formula. And, again, I mean, this trace, I mean, it's some function of Ln. I mean, this trace can be computed by going to the eigenbasis. And then, of course, it's the sum of the eigenvalues. That's just what I've written down here. All right, now of course, you look at this formula, and then it's clear, I mean, I want to have this sort of, this integral should be, I mean, I must have a finite partition function, and therefore, I cannot really allow any kind of this, but, in the thermal case, I mean, the thermal case is the special case where V of W is just 1/2 W squared, maybe with the beta multiplying it. And so you see that I mean, it's sort of, when you look at the other things, I mean, you realize that in order to have a well-defined partition function, you must require that V is confining. Now, how confining exactly? I mean, this is a little bit up in the air, and nobody really knows. But what you should have in mind is sort of basically a potential, which, of course, you can have a lot of variation, but eventually we will sort of maybe increase, maybe linearly or faster than linearly. It should be bounded from below, and so it's a confining potential, okay? And you will see later on, I mean, you will get sort of a more clearer, idea of what kind of potential I can allow, but it certainly must have been something of this type. All right, so now we have... But now we forgot something. I mean, so, I made already this writing mistake. I mean, I started from 0, but actually I really should start from 1. But then there's I told you last time that there's another conserved quantity, which is the stretch. Plus the stretch. So I have to put the stretch also into my GGE. And the way how I do this is that, when I was even mumbling already that these things are, these partition functions are finite. But that's, of course, if I really take it literally, that's, of course, total nonsense, because you see, I mean, you have a potential which increases, I mean, this is a function here which increases exponentially, right? I mean, so, it's something like this. And if I now take this in the exponential, I mean, I will just get infinity. And it's also physically clear that, if I just sort of naively put e to the minus h, then, I mean, the particles will simply, it's a repelling potential, the particles will simply move off to infinity. So it clearly cannot be finite. I mean, so what I have to do, and that's sort of, identical to actually inserting the stretch, what I have to do is if I think about the chain picture, I mean, so here are my chain particles, in order, there's this strong repulsive potential, so what I must do is I must confine them. Now, if you think about fluid particles, you would just put them in a finite volume and then hope for the best when you let the volume go to infinity. But for the chain, I mean, the more natural thing is that you just have a linear force confining the particles, okay? And now you look at the stretch, what I should add in the exponential, well, you see that what I should add is simply the summation over j equal 1 up to n, and then I have here the stretch rj. Well, let's put here n minus 1, that looks a little bit nicer. Well, okay, well, anyway, so I do it like this, and then you see that because it's just the potential differences, what I find is just qn minus q1. And so you see, if I put this up in the exponential, then it just means, in the statistical description means that I'm putting outside here just a constant force which confines the particle, okay? So that's just the pressure, okay? And so what we have to do is we have to add the term e to the minus. Now, there's another parameter which I keep, which is not inserted in this potential, and then there will be the summation over j rj. Okay? And if we do both, I mean, this weight and multiply it with this weight, this gives us the properly defined Gibbs ensemble. And I write this out sort of slightly more carefully. I mean, so first of all, the pressure, of course, has to be positive. I mean, it really should confine. And then I can really write out what is the Gibbs ensemble. So now we have sort of the GGE. So first of all, there will be a partition function C. So maybe I should say this in words again. I mean, so you see now the Gibbs ensemble, the generalized Gibbs ensemble, it has two parameters. One of them is just the scalar, which is the pressure, which has to be positive. And the secondly is a general confining function, right? So that's, of course, because it's a function on R, it's sort of, an infinite number of parameters if you want so. Okay? But from the notation, it's much easier just to think of, of course, V is a function, but, it will be P and V, which are sort of the two parameters which characterize the GGE. I mean, so I sometimes, I put this explicitly, and of course, there's the number of particles, so this is the partition function. And now let me just write it out very explicitly. So, as always, there's like an a priori measure. So I go 1 up to n. So first of all, there are for the momentum, I mean, this is just sort of the integral over dp, and now there comes the integral over dq, which is then sort of, an integral over dr, but then I'm using the Flaschka variable, so it will be actually an integral over the dha, okay? So then there will be, let's see, what did I do now? I wrote it very carefully, because, the Lax matrix, actually, if you really do the counting, then I put zeros everywhere here, so the HJs, there will be n of the BJs, but the first off diagonal will only have n minus 1 elements, right? And so I really wanted to do this carefully. So here I have n minus 1, and then I have j equal 1 to some dha, okay. But now you have to compute the volume element. Now the volume element, I mean, you have to go through this simple formula. So that's an easy exercise. So first of all, what did I write here? Okay. Let's see. Okay. Well, never mind. Okay, so I've written this already for the very. Okay. In my notes, I have it still for the P and Qs. I mean, so let me just do this in one step. I mean, so first of all, when you do this, I mean, you get a 2 over HJ. And then you see, I have the term. I have this term. So it's e to the minus p times the summation over rj, right? And so you see, in terms of Flaschka variables, I mean, that's very easy. You see, it's just a product of these terms, and then I only have to sort of worry about this factor of 2. So it actually will be 2p. Okay, and so you see, in your a priori weight, I mean, you get also the term hj to the power 2p, right? Okay. Now you see, things are fairly nice because you know, I mean, so here I will get from this confining potential, when I take, for instance, the trace L squared, I will get like a Gaussian, and so the integral over the B's, so maybe I should indicate this. I mean, the B J's, of course, are in R, but the H J's, because, you know, I'm doing the Flaschka variable, since the exponential, the H J, the H J's have to be in R plus, right? And so, I mean, this is of course Lebesgue, but then I will get the weight, which sort of like a Gaussian. So this is certainly, you know, will make it finally integrable. And here, you know, I mean, this might be a little bit dangerous, but I've enforced that the pressure should be positive, and therefore, you know, this sort of gives you, I mean, this is something which is actually integrable, and then there will be some weight, I mean, which sort of modifies this. Okay, and so the weight which I have to put is e to the minus the trace. So the pressure I put in already here, and here I have the trace of V of L. Okay, so this is the Gibbs Ensemble. This is the GGE written already in the Flaschka variables.
Can you explain once again where the 2 over 8 takes from?
The 2 over, wait, you mean this one?
No, the previous recap.
Oh, this one?
Yes.
Well, just do the algebra, no? I mean, you know, I go. You see, I have an integral over. Okay. The a is e to the minus r over 2. I mean, so the dA, etc. I mean, just do the transformation of variables, right? No? Okay, I'm not going to do the exercise, but yes, now a question.
Sorry, but I forgot what the exponent p is in your AG to the 2p.
The p comes from adding the external force.
The AG to the 2p is the pressure.
The p is the pressure, okay. Right? And it comes from writing this and realizing that this. I mean, so okay, I did a little slightly more longer. I mean, so this is nothing else but the product over j of aj to the power 2p, right? Yes?
The sign of p. This Toda lattice, the interaction is attractive.
Yeah.
So,
okay. Never mind. I mean, you know, with my it's clear that I want to have here a positive p, right? I mean, you know, whether it's plus the pressure or minus the pressure physically, I mean, you can think afterwards. But you know, if I look at the formula, I mean, I think you don't want to have a negative p here, right? You see, if I put a negative p, I mean, then, you know, this should put you already infinity. Yeah, but I mean, you know, look at the final formula. I mean, then it's clear that I want to have a positive p in order to have a finite partition function, right? I mean, so, and then later on you worry whether physically it should be okay.
The question for the moment is GGE is definition, right?
It's a definition, yes.
So, but because you say things like we must include also stretch, we must include this.
We must include all conserved quantities. That was sort of. Well, okay, that's fine. Then we are in trouble. Yeah.
To that, actually, I forgot. Maybe you mentioned that, but it's somewhere the energy, the Hamiltonian.
Ah, okay. Oh, yeah, the Hamiltonian. Yeah, this I think I put last time, but I mean, let me put it. I actually will come in a second because I will do the example of the thermal state. Yes. No. I mean, but that's a good point. I mean, you know, but the whole generalized hydrodynamics sort of builds on the assumption that we have a complete slit of conserved quantities. Right, you know, if suddenly somebody, you know, we have a model and somebody comes along and say, you know, I found more conserved quantities, then we have to worry and maybe we have to include them, right? But a priori, we should sort of take all, whatever that means exactly. So here, I think for the Toda, we are on a you know, very, very safe grounds that we know that it's actually really all what we, you know, that it's really complete.
Next question, why is it really that we have to include more and more conserved quantities? Why?
Oh, why is it? Well, because you know, I mean, think about this notion of local equilibrium, right? So I mean, so now of course equilibrium is replaced by GGE. Now, you know, I mean, maybe there's a funny constraint in the fluid that you know, maybe I don't know, the temperature is not changing, right? Or maybe, you know, but in general, you know, we have to imagine that the hydrodynamic equations will couple all the fields. You know, there's no a priori reason that certain modes certain fields will be decoupled, right? And so, to be on the safe ground, we should try to include as many as possible. Once I've written down the hydrodynamic equation, then maybe under certain instances, maybe it suffices to consider only certain subsets. But a priori, I should think.
Something that should be like correct hydrodynamic equations?
Correct hydrodynamic equations. Well, I think maybe correct is sort of looks like a teacher, right? I mean, you're making marks. No, but I think people talk about complete, right? About complete.
No, people talk about.
Yeah, no, I think that notion is sort of certainly around, right? I mean,
to understand what is guiding us.
No. I mean, in principle, what is guiding us is that you take the dynamics and you use this somewhat vague notion that we have a complete list of conserved quantities, right? I mean, in principle, if I have a good control over the dynamics, maybe I could decide. But in general, we don't, right? I mean, so very often, this list is sort of based on wishful thinking, right? If you take a strongly interacting fluid and then you say, it's the usual 5 conserved quantities which are conserved, that's wishful thinking. Of course, it's true empirically and it's certainly a correct statement, but to get it from the dynamics, but, finally it should come from the dynamics. Okay, so now let's make the example of the thermal case. Okay, so in this case, I said already, the V is of W is just, so let me forget about the beta, it's just 1/2 W squared. And then I look at this formula, and so you see what I have to compute is the trace, right? Okay, so if I compute the trace of L squared, this is what of Ln squared, well, that's just, so I have to put the 1/2. That's the 1/2, and then that's the summation j equal 1 up. So, the trace is just sort of, the square of all matrix elements. So it's 1/2 up to n, and then I have sort of, 1/2, and then I have the bj squared. Okay. Well, maybe I should, okay, so now I put here the 1/2 bj squared. Well, and now I have to take also solve the off-diagonal elements, but you see the off-diagonal elements are the HJs along this line and the J, along these 2 off-diagonals. And so in fact, I will get +2. That 2 is actually extremely important. That's why I make this example. Okay. And what you find is that this actually factorizes. So in fact, this is a product. And under my GGE, under my thermal Gibbs measure, the X matrix has entries which are independent. That's a very special case, but it's nevertheless good to sort of remember that the thermal sort of is particularly easy, right? If I look at some more complicated things, then of course it will be always right angle, but the entries will be somehow correlated in a complicated way, which is sort of specified by this formula. Okay, so they are independent, but what okay, so let me put this okay, so let me put it here. So this continues the thermal case, okay? So Ln has independent entries. And so let's look at a little bit more independent. So let's look a little bit more carefully at what we have. So for the diagonal, you see it's e to the b squared, and it's just relative to dB. So the diagonal would be just IID Gaussian. Okay? So the diagonal, so these are the BJs. They are IID, so that just means independent, identically distributed unit Gaussians. Okay, so what about the HA? You see, you look at your a priori, it's always the same, so it doesn't depend on the index, so they're also IID. And now what is the distribution which you see here? So you see, you get, you should look at, okay, so distribution is dA 1 over a to the power 2p, and then I have an e to the minus a squared, right? So this is the distribution. Okay, so this has also a name, that's the so-called chi distribution, and the parameter of the chi distribution is the parameter which is sitting in this power here. So it's a chi distribution. It's chi 2p. Okay, 2p is just sort of the parameter of this prefactor. But when you look up in the books, what is a chi distribution? You see that actually it's not relative to the e to the minus a squared, but it's relative to a normalized Gaussian. So when you look up in the books, I mean, you will find that this quantity is called the chi 2p distribution. Okay? And so you see that we do have the factor 1 here, and if I want to use this language, I have to normalize this by 1 over square root of 2. Okay? So it's an IID distribution, and each entry has the chi distribution with the parameter 2p, but I have, the standard definition by what I mean by pi, by chi, I have to divide by 1 over square root of 2. Okay, so let's see what else do we have. Well, okay, then I guess, is that fine enough? Yes?
So this means that if the velocities are distributed like Gaussian, then the position they must have the traditional.
Yeah, sure. It's just saying in slightly different variables the same thing. Yeah. Okay. Okay. So now what do we want to compute? Well, I mean, we want to compute the density of states, but let's do it step by step. I mean, so what we would like to compute is the free energy. So I call this F Toda so that I remember that this is the Toda. Then I put here the P and the V. These are the parameters, and that this would be, of course, nothing else but the limit is n to infinity of 1 over n of minus the log of the partition function Cn of P over V. Okay. Now, it's clear that you will be able to do this kind of computation. Of course, people have done this sort of early on in the case where in the thermal case, I mean, where things just become independent, and then, of course, computing the partition function and computing the free energy is sort of a simple exercise. But now the trouble is that our variables are sort of correlated in a complicated way, right? I mean, there's this weight factor here, and then so, of course, I'm completely stuck. I mean, how can I compute such a complicated object, right? It's an extremely complicated integral. Yeah. And so as life goes, I mean, sometimes one is lucky, and there is a paper by Dmitry and Edelman, which actually in the random matrix community is pretty well known, which was written in 2002. And they do something which is sort of rather close, but not completely identical. And so let me sort of try to explain you a little bit this Dmitry Edelman result. So their motivation was totally different. I mean, they had, I think they still don't know anything about the Toda lattice. I mean, these are sort of, people who come from numerical analysis and wanted to study, how to diagonalize random matrices, and so never mind. I mean, so what they were looking at was a matrix which is again tridiagonal. So it's always an n by n matrix, right? And what they put along the diagonal. So let's see. Okay. So I put it like this. Okay. So diagonal. They put Gaussians IID. That's a good start. That's exactly what we want. I mean, so it's 0, 0, right? What I'm trying to say is they started the matrix, which is rather close to our Lax matrix, but not exactly. And so this is what I want to indicate. Okay. Okay. So what is the off diagonal? Okay. So it's chi. Oh, that's good. In fact, when you look in the paper, you find it's 1 over square root of 2 chi. That's even better. Why is it better? Because you see, I mean, this factor of 2, I mean, we cannot get rid of. You see, I mean, it's the ratio between the kinetic and the potential energy, and it's just fixed by the model. And, I cannot put a 5 here, right? All right, so that's good. But now you look at the parameter of the Chi distribution, and what you find is that in their paper, what you find is they call I take the original notation, they call it also beta J. And beta is some positive arbitrary number. Okay, so you see, in our case, we had IID along the diagonal, always the same parameter p. But now what they are saying is they can look at this matrix, but this parameter is changing linearly. So in my language, what they have is sort of almost our Lax matrix of the Toda, but the pressure which is sitting here is actually changing linearly in label space, right? I mean, so, as I go along, for j equal 1, I will have the parameter beta, then I have 2 beta, 3 beta, 5 beta, etc., etc. Okay, so it's not the same. So we have to worry about this, but this comes next. So first I want to sort of convince you that this is still want to explain here what they can show about this example, okay? Now what they show is that, so the theorem is, so that's a big result. I mean, so there will be all kind of partition function normalizations floating around. I mean, so I will not take particular pay too particular attention to that. So what they say is 1 over n. So it's e to the minus 1/2 lambda j squared. That's already good, you see. I mean, this just comes from the diagonal. I mean, the diagonal are unit Gaussians, and the diagonal are unit Gaussians in our case, so that's fine. So now comes sort of the piece from the off diagonal. And what they say, it's the piece power it's the piece power of the van der Monde, lambda I minus lambda j to the power beta. And that's it. Okay. Now this formula is known to the community, I mean, statistically, the random matrix community as the log gas, as the one-dimensional log gas. Well, I'll leave out the one dimension, okay? So what they are saying is that that very particular random matrix has a joint distribution of the eigenvalues, which is given exactly by the standard formula of a log gas with a confining potential which is quadratic, right? So if I put here beta equal to 2, I mean, this would be sort of the famous eigenvalue distribution of the Gaussian unitary ensemble. And if I put beta equal to 4, then I would have the symplectic. Beta equal 1 would be the orthogonal. And the amazing point about their formula is they have a formula for any beta. Okay? So it's just a result. I mean, I mean, I couldn't, and then, going through their computation would be not very illuminating. I just want to say that this is something which is extremely handy and will enable us to make a lot of mileage on our actual problem, which is sort of the free energy of the Toda case. Okay. So now let's have a slightly closer look at. Let's see, what did I want to do next? Yeah, okay. Now let's see whether we can sort of use this. Now, okay, so now you see we want to compute the partition function. So we want to take this object and want to do all the integrations, right? Okay, so let's try to do that. And let me sort of write out this one formula that's sort of slightly lengthy, but I need it in order to explain you what's going on. I mean, so now I'm writing out the partition function which we want to do. Let's see, I have to think a little bit, but you will see in a second. Okay, so I have the DHJ, F2 over H. Okay, so far, I mean, that's fine. Okay, then, so I'm writing out what is the consequence of this theorem, right? I mean, so I want to, so I'm just writing out, so I want to take expectation, you know, I basically want to, where it is, I want to compute the partition function. Okay, okay, somewhere it's still written. I mean, okay, so I want to sort of write this partition function, but so, you know, that's the expectation value of e to the trace of this LM, but I want to sort of take basically, you know, this kind of weighting factor. Maybe I first write it out and then you can see in a moment what I'm going to do, okay? So now in the Edelman case, I mean, you know, the pressure is changing linearly. I mean, so this is what I have to do, and then I write here e to the minus trace. Now first, in the Edelman, you see, I have, you know, I have this particular distribution here, the diagonal Gaussian, and then we realize that that's just a thermal case. I mean, so I have first one term, which is here the minus 1/2 trace ln squared, right? And then there will be still some other part. I mean, I want to have a general potential, so maybe I simply add to this or subtract minus the trace v twiggle of ln, and you know the 1/2 w squared plus the v twiggle of w would be equal to the actual potential which I'm interested in. Okay, so now you see, they are telling me, okay, so the first observation is, let me write here an E. The first observation depends only on eigenvalues. Because it's a trace of Ln, which only depends on the eigenvalues. Now what they are telling me is that this whole thing, that's this formula. They tell me what is the joint distribution, right? So I can write down what this integral is. Well, and so let me just write it down. So this is equal to, so there is some normalization which depends on V and P, but I mean, let me just put here V, which I don't care about. And then there's the integral. Now just copy this formula. It's a product. Yeah, so it's a product. J equal 1 up to n d lambda j. Okay, and then I have e to the minus. Now you see, you know, in this formula I get a lambda j squared, but you know, and I'm averaging this. So this gives me the v twiggle of the eigenvalues, but they just sum up to the v. I mean, so here I can just put my potential, which I would like to have, which is lambda j. And then there's some interaction, and the interaction is simply this. And now let me sort of write it in a more statistical mechanics way, which would put this up in the exponential. So there would be the e. And well, then there is, you know, here it's I less than j, so there would be factor 1/2. So it's 1/2 over beta, the summation I different from j equal 1 up to n. And then you have the log of lambda I lambda j. So this is why it's called log S. I mean, you have sort of particles on the line which are confining. This is why you need here a confining potential, which are confined by an external potential and which interact with this sort of logarithmic repulsive interaction, right? I mean, so this is the standard, and there's sort of a strength parameter which is beta. So this is true for all beta. It's an identity, all beta, all n, right? And for arbitrary, well, I mean, you know, you see from here that you know what I mean by confining. I mean, you know, the minimal condition somehow is that this integral should be finite, right? I mean, maybe I need a little bit more because, you know, this is strongly repulsive, and so, you know, maybe it should increase a little bit more than just sort of integrability. But anyway, I mean, it should be a confining potential, okay? So I have this nice and beautiful identity. And you see one other thing. You see suddenly the log is appearing here. Remember that the log was the two-particle phase shift of the Toda lattice. And it's no accident that, you know, of course it's the same function, but it's no accident that the log will appear. Because, when you look at the quantum mechanical literature, you will find that when you do, say a few words more later, but, when you do sort of beta ansatz, you will see also the phase shift appearing. And so the fact that I see the log is sort of, extremely sort of gratifying. Now, there's still some question? Yes, yes, question?
So you change from AB to lambda, but what are the other variables? You make a change of variables from A, B?
No, I'm using, I don't make a change of derivatives. I'm using the theorem of Edelman, which tells me that under this measure, he knows what the distribution of the eigenvalues is. You see, it's not just a change of variables. No, it's a deep theorem. You would not see it. If I give you this as an exercise, you wouldn't know how to do it, right? I'm really using this theorem. They tell me that, for that very particular matrix, which looks sort of very specific, they somehow know how to compute the joint distribution of eigenvalues. If I give you, I give you a tridiagonal matrix with let's say, independent matrix elements, you have no idea how to write down the joint distribution of eigenvalues. It's a very singular situation, right? You see, you can say maybe general things or so, but really computing the joint distribution of eigenvalues is completely out of scope. So this is a very, first of all, it's a very specific result, and it's a sort of unusual result that you can actually compute the joint distribution of the eigenvalues. So what I'm saying is that, I think of this as an expectation with respect to this whatever, there are random matrices here. And what I'm saying is that the joint, this depends on the eigenvalues. And so all what I need from this complicated distribution, what is the distribution of the eigenvalues? And they give me the formula, so I just put in the formula, right? Yeah. More questions? No.
It's remarkable that this is true for every fixed n.
Every fixed n, every fixed beta, as you will see in a second. You see, first they did this computation for beta equal to 2, right? And it was only after, then they did it for beta equal 4 and 1. Then there was some break. And then they realized that their computation would go for all beta, right? Okay, so now what, we are not done. Why we are not done? Because, I have now the nice formula, but it's not what we want. Because, you see, we want to have something which is a constant here. But now we have a linearly varying potential. So what do I do? Okay, so fortunately, there's a very simple idea, namely choose. I still have the freedom to choose beta. Choose beta. Let's see. 1 over n times 2p. Okay. And now, rather than rewriting the formulas, let me sort of just do this by hand. So I put here, well, okay, let me put here 1 over n, and I put the 2p in here. And, well, so here I put, this I'm certainly allowed to do because it's true for any beta, right? And now let's look slightly carefully at both sides of this equation. So now let me first look at this side because that's easier. Now I appeal to your statistical mechanics background. So here you have the a priori, which is sort of some nice integrable object. So this is just sort of the a priori measure, and then I have this logarithmic interaction, but it comes with 1 over n. Everybody is interacting with everybody else, but with the strength which goes like 1 over n. This is just mean field. And mean field, we know what to do. So the free energy of this thing, I will write down, but the free energy of this thing, of course, we can do, and we can do for arbitrary v, right? So on the level of the log gas, you see, we are not doing the sort of more complicated log gas where this coefficient is 1. No, it's 1 over n. Okay. So for the left side, you should have sorry, this is maybe the right side, right? For the right side, we have simply mean field, and so we know what to do. Okay, so what about the left side? Well, now we have this sort of pressure which is changing linearly, but you see it has a slope 1 over n. So in each little piece, the pressure will be constant. And so if I'm going to compute this thing here, it will be just the sum of the free energies. What else should it be? Of course, I mean, there's something to be proved really, but it's sort of intuitively it's quite obvious, okay? And so the left side is slowly varying p. I mean, slowly because I was forced to I made this very particular choice. I mean, which is it's slowly like 1 over n, changing pressure. Okay, now we are done. So let me just record, this thing which we have. I mean, so what we find is that and then I'm talking about the free energy. So what we find is that the integral 0 up to 1 du of the Toda free energy. Now it's slowly varying, but it's varying linearly. I mean, so J over n will become u, and it's u times p, right? I mean, so this parameter p is changing linearly throughout the system. And so this side will simply converge to the integral of the Toda from 0, I mean, of this expression, okay? On the right side, I don't put a formula here because I want to do it a little bit better later, but this is the free energy of log gas of mean field, log gas. And there's a confining potential V, right? So I mean, just remember that we have the right parameters. I mean, the strength of the mean field log gas is the pressure, so that's fine. I mean, so that's one parameter, and then there's another parameter which is the confining potential. And you see that in this way, I mean, this many parameters. I mean, the chemical potential sort of enters in a very, very simple way, and that's of course extremely useful because otherwise you wouldn't be so easily do computation. Okay, and then now the rest is sort of simple exercise. So I put here, I just changed variables, so that's f Toda of u, and there's a 1 over p here, so I get p times this thing. Well, and now you differentiate with respect to p, and you get the final result, which is f Toda of p is equal to the partial derivative, because there's lots of other variables floating around, partial derivatives with respect to p, and it's p times what we have here in the bracket. So in the brackets, I have the mean field free energy of that log gas. So this, of course, I will discuss in more detail. So what comes in this bracket will be the next chapter. But what I want to emphasize is that we have computed the Toda free energy, and now you see what I can do at that stage. I mean, just sort of to see how connect up to what I was saying last time. So I mean, once I have the Toda free energy, if I want to compute now the expected value of the conserved quantities of our QNs, it's basically just, variational derivatives with respect to this potential, right? Because, when you differentiate, if I take variational derivatives, we get down this lambda chase, right? So we don't only get the free energy. I mean, out of this, there must be a formula for our density of states. I mean, you can sort of more or less guess already what it is, but nevertheless, I mean, I'm just saying that, it looks as if I only have the free energy, but in fact, I do also have the density of states of my Lax matrix, which is of the central quantity for the generalized hydrodynamics. Okay, so let's see how I am doing terribly. Anyway, but I did this part already. Okay, so I have to watch out. Okay, so maybe I do a little bit more space and then think about these things. So, Okay, so now I want to sort of discuss a little bit this free energy. I mean, I still want to come to the carbons, and so I will do this maybe, slightly catchy. I mean, all these things, those people who really want to see the details, I mean, they can look it up. I mean, it's not so illuminating for the blackboard, and but if I would have another hour, it would be better. Then one could sort of say more about the details. But anyway, I mean, let me just do it somehow the way how I planned it. So the next question, next chapter would be. So this 6 point. This was the density of states. Well, maybe I put it the lex density of state. Okay, so let's look at this mean field formula. Well, I mean, you have to compute. What do you have to compute? Well, I mean, you look at this thing up, right? And so now you want to compute the free energy. I mean, it's already sort of in a density functional form. I mean, so think of the empirical measure of this lambda chase. I mean, then this is when it's just the integral over the lambda, over this empirical distribution with this potential. And here you see, because there's a 1 over n, which is sort of a Riemann sum, and basically you see here that, this double integral appearing. And of course, I still have the d lambda chase, so there will be an entropy term over here, and different from sort of standard random matrix theory, where you have something which is order 1 here, and the entropy is sort of subdominant. Here they are all on the same of the same size. So I will have 3 terms to my mean field free functional. But then there's one observation, the p enters sort of in a very simple way. This is sort of quadratic, and the p appears here, and so I can sort of shift the p somewhere else. And so let me just it's a simple algebra, so I'm writing down the final formula, which is sort of comes out of this thing. I mean, so I'm writing now the mean field variational formula, right? Now the free energy will be then the minimizer of that variational formula, right? But I'm just sort of writing down the density functional. Okay, so I'm just sort of writing more explicitly what I said very quickly in verse. I mean, so I have a dw. So this is sort of asymptotically the density of states. I mean, so that's just a rho of w. So that's not yet the lex DOS. I have to minimize with respect to these objects. Okay, and then that's the v of omega. Okay. So that's just the Riemann integral corresponding to the first term. You see, the first term, there is a sum. I mean, I put it here as a product, but upstairs I have a sum. Okay, so maybe I'll write it. This simply is a continuum approximation to the sum j equal 1 up to n of v of lambda j, right? I mean, this is what it is. Okay. And if these roots appear with the density rho w, I mean, that's what you get. Okay, and then I shifted the p somewhere else. I mean, so it will not appear over here. Then there will be a double integral d omega prime, and then there's the log of w minus w prime, and rho of w prime, and then there will be the entropy term, which is the integral over dw, and there will be rho of w log w. And since I shifted, you have to minimize over all rows which have a density. So they have to, these functions have to be positive. But now the normalization has been shifted, and the normalization is that the integral over dw rho of w should be equal to p. I mean, so this is where the pressure enters. What?
Normalization.
Well, depends. You should depend also on v, you mean? Or?
goes first to theta probably?
No, no, it doesn't. Actually, it depends. It only depends on P, yeah.
Normalization of their joint distribution of eigenvalues.
Well, I mean,
The set there is probably
no. I mean, well, I mean, no. I mean, you know, but the beta is also depends only on P, right? I mean, so. You know, I put beta equal to 1 over n2p, right?
does it contribute in this equality to it? That there is also another logarithm of the d and p that you have to look at?
Yeah, sure. I mean, this will be just some number, okay. Some log p or so, some trivial number. Yeah. More questions? Okay. So let's see. So now you have to minimize this object, and then more precisely, you know, the Toda free energy. Let's say of P of V is so let's call the minimizer the minimizer, which is actually unique, but anyway, I mean, so let's call this rho star, and then what I have to do, I mean, that's just a formula, that's dp, and then I have to do p, now the p has gone out because I put it sort of elsewhere, and then it's f of rho star, right? I mean, so this is the final formula for the Toda free energy. And now it's clear that you know, once you have such an explicit representation, there are lots of things you can do. I mean, for instance, now finally we get an equation, because, you know, I can now look at the Euler-Lagrange equation. And so, you know, rather than trying to figure out the minimizer, just writing down what is the condition for the minimizer. Now, there's a constraint, so there will be a Lagrange parameter, which I call mu. Okay, and then I have to do, you know, sort of this variation formula, and I can write down a closed equation for them. Okay, so let me at least sort of write down for you the Euler-Lagrange equation, because I mean that's something which is going to come up very quickly in the other talks. I mean, so for this it's convenient to introduce an operator which acts on functions. And it's just sort of our famous logarithm, so that's an integral over w prime of log of w minus w prime, and then I have here psi of w prime, right? I mean, so that's a linear operator. It just sort of abbreviates the previous my notation, okay? So let's do this variational derivatives, and what you find is then, so this is now the Euler-Lagrange. Now the variation derivative with respect to this one is very easy. That's just a rho, and here you have a quadratic one. So you know it's not too complicated. I mean, so let me write it out sort of with this operator, because then it becomes sort of a little bit shorter. I mean, then I have a t, and the function which enters into the Euler-Lagrange equation. So this is the Euler-Lagrange parameter, and the solution of the Euler-Lagrange is denoted by rho mu, right? I mean, so this is why the rho mu appears here. And then it's minus t of rho mu. You know, there's a 2 here. You know, here I have a 1, and there's a 2 here because I'm differentiating a square. And then there will be, of course, the entropy, which gives a plus log rho mu. And then, because, you know, I have the mu, I also have the variation of that. I mean, so this means minus mu. That's come from the constraint, and that's 0, right? I mean, so this is the Euler-Lagrange equation, which, you know, in other fields, people say, okay, you know, the rho mu is sort of something like a Boltzmann factor. I mean, so very often, I mean, one writes the rho mu as e to the minus epsilon. I mean, these are functions, and so these epsilons are sort of the quasi-energies, if you want so. Okay, and then now, rather than writing it in terms of the rho mu, you can write it in terms of the epsilon. And you see that this is a simple exercise because, you know, basically out of the log, I mean, you get the epsilon. And when you do this, I mean, you get the equation, which is usually written as epsilon equal v minus mu. And then there's minus t, and now this operator acts on this exponential function e to the minus epsilon. Okay? And that's sort of the classical analog of what people call the thermodynamic Bethe-Ansatz. So for quantum models, you will find exactly the same equation, only the function e to the minus epsilon is typically replaced either by the Fermi or by the Bose-Einstein distribution. So you know, I mean, here, I mean, using for this Bethe-Ansatz sort of doesn't make any sense because nowhere in my argument there was any Bethe-Ansatz. But the main point is that you know, fortunately due to this theorem of Dmitry and Edelman, at the end of the day, I mean, you get something which you know, is sort of the expected structure. I mean, and it's sort of, you know, sort of the same structure as you find for many other integrable systems, be it classical or be it quantum mechanically. So if I want to do, for instance, the hard-rod gas, I mean, then you know, the log, of course, is sort of replaced by the characteristic, you know, just sort of a constant function, and then you work out the result, and then of course you get exactly what you can sort of do by other means. Okay. Okay, so let me just sort of say only one more point on this is that now we want to do well, let's see. Let me first have a look. I know maybe I can still state this. So now, of course, you know, now you can do a lot of identities, which in fact, for those who are not familiar, you know, they're more confusing than illuminating, right? Because now you have equations, and now you can manipulate these equations, and then you got, but you know, this will go very quickly, and so you have no advantage of this. So maybe I should sort of state two identities which sort of come out of the fact that we now have a variational formula to look at, and one identity is that I can rewrite the Toda free energy. Now I put here P, but you know, it should be P and V. It's in fact nothing else but this Lagrange multiplier. Okay, and that's very convenient because you see, for instance, if I now want to know I want to maybe differentiate this Lagrange multiplier with respect to P, then I only have to differentiate the Toda free energy with respect to P, and that's of course nothing else but the average thresh, right? I mean, so if I compute, for instance, dp of mu, this is nothing else but the GGG average of the stretch. And you get lots of identities of this thing. Okay? And the other thing which maybe I should mention also is, you know, I put here the lax DOS. I mean, so how does the lax sort of appear in this kind of formalism? Let's see. Let's make a little bit more space here. So how do I compute? Okay, so let me say sort of the philosophy. I mean, so the philosophy is saying that you know, I mean, one sort of regards the Euler-Lagrange equation. One regards this sort of as the basic object. Right? I mean, this is an equation, you can work with this, and so you somehow imagine that somehow by some or other methods, I mean, you are able to really obtain the solutions of the Euler-Lagrange equation. And then the question is, you know, having that solution, what are the other objects which are interesting, in particular those which we sort of would need for you know, writing down the generalized hydrodynamic equation. And so there's one identity which you can do, and so you define something which is called, again, you know, so I have to put here some color because there are too many P's, but you know, I'm just using sort of a standard notation. I mean, so I put here a P. So this is something which in the quantum context would be called the particle density, which is sort of fine, or quasi-particle density. Okay, but in our context, I mean, you know, this rho P is nothing else but the partial derivative with respect to this Lagrange parameter, right? I mean, so I can do this. Okay, now you see, you know, if I want to get the density of states, you see, I always have to do this funny differentiation, right? I mean, so you see that there are always sort of this dp appearing. I mean, also here, you know, when I want to compute what is the Toda free energy, it's not just the mean field energy. I always have to sort of do this derivative with respect to P. I mean, that comes from this linear ramp. And so this, of course, you know, translates into this thing. I mean, so when you look, so let me call this average equal to nu. You look at the constraint, and then you find that the integral over the rho P times nu times rho p. I really have to use the color because, you know, it has nothing to do with the pressure, and from the distance you cannot distinguish small letters and bold, you know, sort of Roman and italic and all these things. So anyway, so this happens to be normalized to 1. And then, you know, if you sort of want to identify, you have to sort of actually compute variational derivatives with respect to the confining potential. And then if you do this, then you get the final result, which is that, you know, what we call rho q. So this was the DOS of flex. Yeah, just one moment. I mean, let me just do it out and then we can discuss. And the result is that this is nothing else but this quantity rho p. Okay? So now we have sort of, you know, reached the point that we actually have a formula for the density of states of the Lax matrix. Okay, now comes the question. Yes. You mean this one? Yeah. Well, I mean, so epsilon is a function of w, right? So this is a function of w. This is a function of w. This is just a number. This is the operator t, which I erased. No, here's silver. Here's the operator t acting on some function. Now this happens to be the exponential function. No? I mean, this means the linear operator t acting on the function e to the minus epsilon of w. Yeah.
This is an exact result in large N? Is this an exact result in large N?
Yeah, that's an exact result in large N, yeah. You know, I mean, all these things, I mean, you can put sort of, you know, I mean, you know, if you want to do exact results, then you have to start talking about condition and all these things, but, yeah, it's an exact result, yeah. Yes?
So mu was the conjugate parameter.
That's right. I mean, mu is the Euler-Lagrange parameter, right? To p, exactly, yeah. Because the p, you know, the p is the constraint, right? And so this is why the mu, of course, has to appear in this thing. So, you know, what you have to do is you have to find the solution. I mean, the usual variation thing. We have to find the solution to this equation, and then you have to adjust the mu in such a way that you satisfy the constraint, right? Okay. Exhausted? No, every sort of. Okay, so let me just summarize in word. I mean, so the big point about this computation is that, you know, what before was extremely vague, now we have a very concrete idea of what you know, this object actually is. And you know, I have to sort of remind you of you know, what the idea is. I mean, so we have here the GGE, right? Now what I sort of somehow explain to you is that you know, there's this object rho p, which is sort of I mean, the particle density, which of course depends on v of p, you know, of this particular GG. But now and this rho p is sort of now, you know, for this we have a very concrete prescription in terms of all these equations over here now as a solution of a variational problem. Okay, and now what we would like to do is from the GGE, of course, we also must get the currents, right? The current DOS, so to speak, right? And now the idea is that, you know, if we could do this error with the same explicit formula as I had here for the conserved charges, then of course, you know, that will automatically give us what is the relation. You see, we wanted to get the currents as a presumably complicated function of the rho p's, but if you could, you know, sort of also compute the currents, you know, in this way, I mean, then we would be done. I mean, then we can write down on our hydrodynamic equation because, you know, the rho p I have, and then I get through this sort of errors, I get this nonlinear sort of functional for the currents, and then we are done. Okay. Now the trouble is that this we don't know how to do. At least I don't know how to do, and I mean, maybe not so many people have looked at that, but I certainly tried, and you know, I don't know how to do it, and so. So we have to sort of think about something else in order to get our hydrodynamic equation, right? Okay. So on this side, we are in very good shape. I mean, I have here in my notes still the example of, you know, what the rho of p looks like for the quadratic case. I mean, that's fine. There are papers on this. For the quadratic case, there's actually exact solution, so you can write down a formula for the rho p, which is not too complicated. You can discuss how it behaves for small p and for large p and all these kind of things. But since time is sort of running, I mean, maybe I just omit this, and I sort of want to still concentrate, on this issue over here. Okay, so let me try to do this. That's the last chapter. So this is now 7, I guess 7 according to my notation. Currents and effective velocity. You see, these things are perfectly well defined. You see, I just, I know what the current function, what the current density is. So there's just some very well specified local function. I just have to take the GGG average, but I just don't know how to do that average, right? I mean, and the point is, I mean, maybe I should explain this. I mean, why can I use these things? I mean, you see, the current had this funny L off, and so the current is an object which does not depend only on the eigenvalues, but depends also on the eigenvectors of the Lax matrix. And the Dmitry Edelman just tells me nothing about the eigenvectors. I mean, it's just, it's just not there, right? I mean, maybe somewhere there is some information, but I never could figure out whether it's really there. Okay, so let me try to sort of come to this this chapter here about the currents, and clearly, when one has to do some argument which does not rely on a too explicit computation. And there's another part which, of course, I cannot sort of convey here, but maybe sometimes mention in other talks, is that for some models, I mean, the formulas which I'm going to write down maybe will look sort of more convincing. Anyway, so let me just sort of try to do what the idea is. So we go back to the fluid picture. And so now I have all these particles moving in R, and so I fix my background GG. I mean, so this is somehow given. So you could imagine that a time t equals, so this is x, and this is time. So at time t equals 0, I just put my GG, I mean, with some confining potential, kind of confining chemical potential and some pressure. And then I simply add an extra particle at the origin. And I assume that this has a definite velocity, which is called v. And so. And now this particle will move. And as I argued, I mean, it will sort of make right jumps, and then once in a while a left jump. But at least we hope that it will sort of, this takes a little bit of time, so it's not instantaneous. But anyway, I mean, there should be sort of stretches where I can identify, we don't care what the label of the particle is, but we want to identify the object which has the velocity v. And this we hope, I mean, we can do with sufficient precision so that this picture makes sense. Okay. Okay. Now the GGE has this particle density which is rho p. That's the one which comes from this variational problem. And now what I want to compute is what I call the V effective. Of V. I mean, so this is really the argument, and it's just of the object. And the V effective is just saying that I want to. I sort of average over all this, over all these things, and then I will get sort of some on average. I will get sort of a law of large numbers. I will get some trajectory which is sort of moving with V effective, right? I mean, this was the initial V which I put in, but then to the collision it will be changed and will be sort of V effective. Well, so what is it? Well, I mean, the V effective is equal to V. Well, then I have to somehow estimate, how many jumps I have to the right and how many jumps I have to the left. Now, you see, how much I jump, I know that's the two-particle phase shift. Okay, so let me write down first an integral over all w's, because you know, in this background GGE, I mean, there will be, you know, it's a function of W here. You know, there will be, you know, all kinds of sort of, you know, I mean, all kinds of components will be a full distribution. So I will have to sort of integrate over all these quasi-velocities. Okay, well, then there is sort of the phase shift. So this is by how much I jump. Okay, well, and then you know, I mean, if I have a collision with some other quasi-particle with velocity v, I mean, this will be the distance which I jump. And now I have to know how often. I mean, so I have to put the weight, right? And so the weight will be, well, first of all, it depends on this particle density. I mean, that's sort of, you know, like what you would do for a gas or so. I mean, so I put here the rho p, right? I mean, so I have to say how many there are. Okay. Now I'm moving. If I want to compute the weight, I mean, then it will be the difference in velocities, right? I mean, you know, if I have a medium where the particles have velocity w and I'm moving through it with velocity v, then the number of collisions will be just proportional to the difference, right? I mean, so.
Why is W a velocity?
Well, I mean, I call it differently. It's just a spectral parameter. I mean, you know, I'm just sort of, you know, the point is that you know, in this GGE, you know, the GGE will be specified by a distribution, right?
Yes, but I never thought that W would play the role of the velocity.
Well, once you're sort of on this hydrodynamic scale, it really looks like a velocity, right? I mean, so, you know, it's sort of slightly, you know, it's a usual thing. I mean, well, okay, let me go into it. Maybe I can explain you sort of later on. Okay, now I put here the velocity difference. I mean, so there will be effective velocity of the colliding particle minus the effective velocity. You know, because I mean, if I compute the weight, I mean, you know, of course I have to take the effective velocity because they tell me how often it actually will collide with a partner, right? And so this is effective velocity v, and that's already the formula, right? Okay, so this is the phase shift, and this is the rate. How often this happens per unit time. But now you see that there's no reason that this is actually positive, right? I mean, so maybe you're saying, maybe you've made an error, but in fact you didn't. I mean, what I really should have written is I should have written here, you know, I mean, if I call this argument x, what I should have written it sort of is really x absolute value. Then it's positive, but you know the phase shift. You know when you do the counting, I mean you know there's also a sign. I mean you know it's going to the right or to the left, and so you know when you do this argument more properly, I mean then you see that it's an x over here. But you know there's another sign of this difference actually sitting over here. And if you do this computation sort of into 3 steps, I mean then eventually you just arrive at that particular formula, right? Okay. All right, and so now what we have gained is, first of all, you see, I have to specify what is the particle density. That sort of is a characteristicum of the background, and what I have gained is a linear equation for V effective. Okay. So you simply assume that, right? So I just want to do it, you know, at that slowness because I think that that's a very central sort of input into this into this generalized hydrodynamics, because you know this will give us now. Well, I mean, once we have this, then of course we get also this function over here. Okay, and you know, in some models you can verify, and in some other cases. You know, you just believe, but you know, you can sort of indirect confirmations. And in fact, you know, with Vir and so we wrote a recent paper where, you know, I was always worried about this formula, and I said, well, look, I mean, for the Toda lattice, everything is so explicit. I mean, why don't we just check the formula numerically, right? And so what we did here is, I mean, let's say we took the thermal case, So this is trace ln squared. So it's just the IID case, so it's just very simple, but we look at the complicated observable, right? I mean, so it's not a very simple thing to do. And of course, the rho p will be some fairly, I mean, it's explicit, but it's some fairly complicated function. Anyway, so now we determine, well, I mean, we determine numerically what is in this case, what is the rho p? Okay. Well, once he has the rho p, I mean, he determines numerically what is the effective velocity, right? And so this, I mean, I give you the rho p. I mean, you have to solve this linear integral equation. There are other formulas by which you actually solve it, but let's assume you do directly this one. Numerically, you do something slightly different. I mean, also the question how you actually get the rho p is a different issue, which I cannot explain here. But in any case, I mean, so you solve this equation, okay, and then we have the rho j from generalized hydrodynamics. I mean, it's some function of W, and for some parameters, and we have plots, and we can look it up in the paper, but just to give you some idea. I mean, so this is the rho j, and it will look something like this, and so it's sort of a piece, and then goes like this. So well, it has a more interesting structure. But anyway, I mean, sort of, you should not think of something that actually sort of has never mind. I mean, so it has to be integral 0, and in fact, there's slightly more exciting structure. But anyway, I mean, it's not very important. I mean, so you can think of this.
What is the logic or how do you go from the effective velocity?
Okay, sorry. Okay. So I didn't say that. Okay. So sorry. I mean, this is of course a mistake. So the rho j. Okay. So the rho j is actually just simply the effective velocity. I mean, effective velocity times the density. Sorry, no, this I just overlooked. Okay. But now there's another transformation. You have to go. This is computed for the fluid picture. And you have to go to the lattice picture, and then you realize what you have to subtract is the mean velocity. I mean, so the correct formula is this one, and the Q1 is nothing else but the integral over W. So this is that's effective velocity. Okay.
That's like theorem or
No. This all what I'm writing here is sort of more or less on that level, except that people are not satisfied with just writing down this equation. I mean, they are checking this equation because you can't there's no such explicit computation as I showed you for the DOS of the Lax matrix, right? I mean, this is something on a mathematically totally different level, so to speak. But people believe in such formulas also for other models, and then of course they avoid and then they try to make check. And so I'm trying to tell you what is the check in the case of the Toda. Okay, so let me repeat again. I mean, so first of all, I look at the thermal case. Then for the thermal case, there's an explicit formula which is used, but we don't use it. But anyway, I mean, so we compute numerically what is the particle density. That comes sort of out of this variation problem. So we have this one. Now I can plug it in here. I can sort of solve this linear equation, and I get the V effective as a function of V, or let's call it of W. I put here the parameter W. Okay, and then out of this I get the carbon density. It's that density which enters into the generalized hydrodynamics.
It states that the density of states for the current is proportional to the density of states.
Well, that's just like for particles. You see, I give you the density, and then you ask what is the carbon? It's the velocity times the density. That's it. There's nothing strange about it. It's the velocity times the density. That's what the current is, right? Yeah, it is just really on that level. Yeah. No, I don't think there's anything strange. Okay, so let me still sort of describe a little bit what we have done. I mean, so we do this computation, and then we get a curve which sort of looks something like this. It has to be symmetric in our case because the average momentum is 0, and so okay, so we go like this maybe, okay. Yes. You mean how do I get this one? Yeah. Well, so this you have to look up the paper. I mean, I can not give a sort of quick answer here. You have to look up the paper of Benjamin. I mean, he sort of worked this out in great detail. I mean, the point is that you see this argument, as you can see from this picture, I've done in the fluid picture, but now you have to go from the fluid to the chain. Everything else was always done for the chain. And of course, they're in some sense identical. I mean, it's sort of, the same thing. I'm just looking sort of from two slightly different point of view. So there must be a relationship, but you have to think a little bit about this relationship. And when you sort of thought about it carefully, I mean, then you see that it will be this kind of relationship, right? I mean, so this minus Q1 comes from going from the fluid to the lattice. Okay, so now how can we convince ourselves? Yeah, I'm finished. I mean, so. Well, I mean, look, I mean, I told you all the time that on the microscopic thing, I mean, now it's already gone far away, but on the microscopic thing, of course, I can compute the moments of these things, right? I can compute the DOS. I mean, so now I just sample according to the thermal distribution, which is an IID. I just sample my Lax matrix. Let's say 300 by 300. I put IIDs on the diagonal. I fix the temperature, so I know what the variance is of the Gaussian. We can of course vary this. I put the chi distribution on the off diagonal. There's the pressure. Of course, we can fix some number. I mean, we can vary that number and check whether it, these things depend on pressure. So we can sort of sample this for various pressures. And then we can just directly compute what is sort of what I call the current DOS, right? I mean, that's just sampling. And of course, we have to compute the eigenvectors because it depends on the eigenvectors. I mean, you don't remember the formula, but I wrote down you the formula, how the eigenvectors appear. So numerically, doing this, it's not 300 by 300. Is that then you sort of, you do sufficiently many numbers of samples so that your noise is sort of sufficiently small. And then you get, and then when you look at this curve, and when you look at what you get from so this is one thing, and the other one is the Keiji Toda, and what you get is sort of, I mean, I guess we'd have dots in our papers, but this sort of lie, I mean, just on top of the curve. I mean, there's just no question that it doesn't show no deviation whatsoever. And then we vary the pressure, we vary the temperature. I mean, we also put the term trace into the power 4. And whatever we do, it always looks like this, right? And so, I mean, on that basis, I still have no idea how to sort of get a better mathematical argument, but I mean, at the moment, I'm really convinced that this is simply the correct formula. Okay, so I'm finished, but so let me put here whatever 8 or what do I have here? Just let me put this is 8. So let me do the conclusion, which is just writing down the generalized hydrodynamics. And so all what I'm doing is writing you for just the equation, which you somehow know already, but now I just want to put it still in full glory. I mean, so first of all, we had the equation for the free volume for the stretches, and that was dx. It's the Q1 which appears here, which is equal to 0. So Q1 is the first moment of the density of states of the Lax matrix, and then the second equation, as promised, is for the density of states of the Lax matrix. So this is this is my rho Q. Well, okay, maybe I write it in the usual way. I mean, U times rho P. This is actually the rho Q. Okay, and then there is a plus dx. Well, and now I just put in this current. I mean, now it's an explicit function of the rho P. I mean, it's sort of slightly, it has to go through this root, but nevertheless, it's sort of quite explicit. I mean, so it's the V effective minus Q1. Okay. That's the end of the story. Now, of course, now maybe you want to know something about these equations, but that sorry, sorry, that's even wrong. Yeah, sure. I get it. Okay, so of course, I have to put in the full thing, right? I mean, so you know, I have to put in this one also, right? I mean, OP. Okay, now I think we are okay. Okay, so of course now the next chapter is, you know, can we say anything? How useful is that equation? You know, these are all so secondary questions. But all what I want to say is that this is the carbon status, and you know, the evidence which we have is sort of very strong evidence that this is the correct hydrodynamic equation for the Toda lattice. Okay, so thank you very much for your attention.
Since
Hello. So in this problem, you have a set of conserved quantities which you can generate systematically from this L matrix, and then you have an extra one that you have to find by inspection. How common is that? Is it that this is the situation, that you have extra conserved quantities that you in general, in other problems?
How common is this equation?
No, I was thinking of the very setting of the problem. So you have a set of conserved quantities which you are able to generate systematically from the L matrix. And then, but you need to manually add an extra one.
But you see that the L matrix is already sort of something, I mean, I guess appears in many integrable models, right? You see, yeah, okay, so it's a vague question. So my vague question is sort of course, you know, there are similarities with other things, but I want to emphasize that, you know, what I call here, the, you know, I mean, the L matrix, of course, it all comes because sort of Lax somehow introduced this concept. I just want to say that the Lax matrix, what I'm using here sort of looks to me like a much simpler object than, you know, sort of the Lax matrix in sort of in quantum integrable models, right? I mean, you know, yeah. I mean, generically, you know, this sort of somehow connected to the thermodynamic beta answers that somewhere there are some Lax matrices sort of appearing, right? I mean, so now you ask how general. I mean, I don't know. I mean, you can just list the models and sort of look up the evidence, right? And I would say, you know, whenever somebody is able to analyze an integrable model, then some of that structure appears, right? So.
Something like an equivalence of ensemble.
Ah, okay, good. Yes,
will
yes.
apply eventually the ergodicity.
Yeah.
You know the Fanny system is, you know, what is the microcanonical measure?
Yes. Yes.
If you know how to converge to the canonical, to this
yes.
GGA, you will have ergodicity.
Yes. Okay. Yeah. Okay. Now, but this is of course okay. Always these things sort of remain to be done to some extent, right? So I'm sort of, you know, when I write down my e to the minus beta h, I naively assume that I have equivalence of ensembles. Yeah.
But do you expect that this is...
No, I certainly expect. I mean, so you could also ask, you know, how much of what I've written sort of, you know, can I really support? Now, let me give a positive answer to your question. You know, the part, maybe I haven't worked out, you know, all the epsilons, but the part which I have done some of it, but the part which I didn't look at the equivalence ensembles very carefully. But the thing which one can do is actually assume that your, what I call chemical potential, is actually a finite polynomial. Then you have a one-dimensional system with a finite range interaction. And for this, you could do transfer matrix, right? Of course, you know, your matrix is sort of slightly complicated, but then nevertheless, I mean, you could do transfer matrix. And that's, you know, this actually, you know, when you do this linear pressure problem, I mean, you have to use transfer matrix if you would really want to get sort of good result. And my conjecture would be that, I emphasize the strictly finite range. Then I think for that case, presumably you or maybe other people who are familiar with proving equivalence ensembles, I mean, should be able to do it. Now, what is for me sort of an interesting mathematical question is whether you can go beyond the finite range. You see, clearly, you know, the potentials which I get at the very end, you know, for my log gas, you know, they are certainly not necessarily finite polynomials. Of course, usually we just write down x squared on x to the power 4, right? But you know, for the limiting answer, I mean, the class of potentials which you can allow is sort of, you know, much more general. But then we get into muddy waters because, you know, of course, you know, if it's just a smooth function, then, you know, it will have some tails and anyways. So then there are a lot of interesting questions to explore, yeah.
I have not seen whether there was explicit rescaling here of time and space, but maybe that's in the fluid picture that one should imagine that, or
well, no,
the usual Euler
I mean, so what I know, that's a good question. So what I've written here down is the analog of the Euler equations.
Yes.
So if I really want to state a, you know, let's say a precise conjecture, I'm on the lattice, I'm just doing ballistic scaling. Mm-hmm. And in the ballistic scaling, I mean, you know, I should get these equations. Yes. That would be sort of like, you know, proving the validity of Euler equations starting from a fully interacting system.
But this rescaling we have not seen yet, right?
Well, I mean, I just want to get the right equations. But you know, if you want to state a precise conjecture, it's the Euler scale. And then, of course, you could ask, you know, whether there may be Navier-Stokes convection.
Yes, that would be my second question. Is there
there are papers. I mean, this is what Dobushin has done already for the hard-rod gas, and then based on this, and you know, other sort of intuition. I mean, people have sort of a pretty clear idea of what kind of next convection you should do there. There's non-zero entropy production. There are non-zero transport coefficients. I mean, all kinds of things.
So I had one question. Yes. So somehow this W, I mean, the reason it's a velocity is because it's, so basically the eigenvalues of the lax matrix, they kind of give the quasi-particle picture, is it? I mean,
yeah, I mean, you know, okay, yeah. I mean, one way, okay, so in what sense are these velocities? Well, I mean, okay, I mean, one, I guess, some people like to sort of, you know, compare this with the rho W. I mean, something with the Boltzmann F function. You see, the Boltzmann F function is a function of position and time. I mean, that would be sort of the space-time point which I label, and then it's also a function of the velocity, right? And then because it's an ideal gas, I mean, you know how to compute the average momentum. It's just the first moment of the Boltzmann F, right? I mean, you know what is the density. It's just sort of the zeroth moment, and then the first moment is the integral over F, and the second moment is the integral over 1/2 V squared, right? I mean, so these are the kind of things which you know. And now you look at this function here, and then you ask yourself, what is the average momentum? Well, it's just the first moment of it, and then you ask, what is the average energy? And of course, the energy itself is something very complicated, but once I'm on that level, the average energy is just 1/2 of the second moment. And so you can think of these things that, you know, computationally, you know, eventually you can think of this sort of like, you know, it's of course, it's not a transport equation, you know, it's sort of a hyperbolic conservation law, but you can think of this function, you know, it comes from somewhere, but once you have the equation, you can sort of think of the W essentially as a velocity, right? Yes, maybe you can add some more.
So basically, if you look at this particle problem, asymptotic, just let the particles evolve and separate from each other. The eigenvalue characteristics are with momentum.
Yeah, that's another point, yeah.
I still don't understand how that picture is related to integrability. So the question of aerodynamics of expressing the current in terms of the density is like the main part of aerodynamics, right?
That's exactly what I do here, yeah.
But this part is this fluid picture.
Well, but you know, I mean, the fluid and lattice are sort of equivalent, right? I mean, so you know, I mean.
How the current is expressible in terms of the density is somehow the heart of aerodynamics.
Yeah.
But I haven't understood how integrability helps, except when you already have these equations, and then you can of course compute the density of states via the GGE.
No, I mean,
I'm not familiar enough with integrability, or this quasi-particle picture is very much linked to integrability.
Well, no, I would phrase it differently. I mean, you know, the fact that I'm even writing down such equations, you know, can be done only if, you know, could be imagined only if it's an integrable system. I need an infinite number of conservation laws. You see, this thing tells you that there's an infinite number of conservation laws. You see, it's a coupled system. I mean, you know, where are they? It's a coupled system. It's an infinite set of conservation laws. I mean, so this means that, you know, if you just look at this equation, you ask yourself what physical system it describes. I mean, you will be immediately led to the case.
Right-hand side
yeah.
here, in the fluid picture, of course.
Well, same thing. I mean, in fluid picture, there will be the same equation. I mean, it will be essentially the same equation. I mean, it's not different.
You're talking about the first equation, that is the integrability equation?
Yeah, sure. No, I mean, the fluid and the lattice is sort of, you know, it's just sort of slightly different coordinates. It's nothing more, right? I mean, you should not think about this sort of like two different things. It's just sort of.
Okay, so let's break for coffee. Let's thank Herbert again for his lecture.